Hello students, in today's lecture we'll be studying about sampling distribution of a statistic and unbiased estimate. Since this is a slightly difficult topic, I would be going in a deliberate manner to clear the concepts in a simple language. Before starting this lecture, I'll request all to please go through my previous lectures on sampling and parameter and statistics. So let's start with today's topic. Suppose we have a population and we want to calculate its parameter such as population mean or population standard deviation, etc. As we have discussed in the previous lectures, since it is difficult or impractical to work with the population, we will take a random subset of the population, that is a sample, and calculate the statistic. Then we will use this statistic to calculate the parameter. Now let us first see how many samples can be drawn from a finite population. Consider a population size of capital N, sample size of small n. Then the number of samples that we can get, we can represent it with a small k. So if we consider simple random sampling with replacement means once we draw an object in a sample, we again replace it with the same object for our next draw. Here the formula for number of samples k is given by population size raised to sample size, that is capital N raised to small n. So if we have a population size of 3 and sample size of 2, then the number of samples that we will get is 9. Coming to simple random sampling without replacement means we will not replace the object that we have once drawn for the sample. So here the number of samples that we will get is given by capital N combination small n, which is equal to n factorial upon small n factorial multiplied by n minus n factorial. So if the population size is capital N, that is 3, and sample size is 2, we will get a number of samples as 3. For now on, let us only consider simple random sampling with replacement. So here the number of samples that we will get is 9. Note that the statistic that we will get for each sample may not be same and might have different values. Now, as discussed during the beginning of the lecture, we want to know the distribution of these value of statistics that we will be using to estimate the parameter. This distribution is called as the sampling distribution. Now let us consider a small example. Let the height of each person be 6 feet, 5 feet and 4 feet. So the parameter, that is population mean, will be 6 plus 5 plus 4 divided by 3, which is equal to 5. Now let us come to sample 1. Here the sample mean is given by 6 plus 6 divided by 2, which is equal to 6. So sample mean, that is x1 bar, is equal to 6. Similarly, we will get the sample mean for rest all samples. Now let us make a table for these values. Let us see the frequency of these values. So out of 9 times, 6 is occurring once. So the frequency of 6 is 1 by 9. Another way of explaining this is that if we take a random sample of sample size 2, there is a 1/9 chance of getting a sample mean of 6. 5 is occurring 3 times out of 9, so its frequency is 3 by 9. Similarly, 5.5 and 4.5 is occurring 2 times, so its frequency is 2 by 9. 4 is occurring only once, so its frequency is 1 by 9. Now let us plot these values of statistic mean against its frequency. 6 is occurring 1 by 9 times, so let us plot the point. 5 is occurring 3 by 9 times. 5.5 is occurring 2 by 9 times. 4.5 is occurring 2 by 9 times. 4 is occurring 1 by 9 times. So now what you get here is the sampling distribution of sample mean for sample size is equal to. You can get similar sampling distribution for sample variance, sample standard deviation, sample proportion, etc. An interesting fact is that if we have sufficient data, then the sampling distribution will be normally distributed. Now let me again show you what is the importance of this sampling distribution. We had seen that the population mean that we had got earlier was 5. If we now calculate the sample mean of all the samples, we get a sample mean of 5, which is equal to the population mean. Thus, as we have discussed before, since it is difficult or impractical to work on the population, we can take sample and calculate the statistic to estimate the value of parameter, thus saving time, effort and money. Hope you have all understood the meaning of sample distribution now. Now let us come to unbiased estimate. Suppose you have a population and you want to calculate its mean. As we have discussed earlier, since the population size is too large, it is difficult or impractical to calculate its statistical constants. So what we will do is, we will take a sample out of this population and calculate its mean. Then we will use the sample mean, that is a statistic, to calculate the population mean, that is a parameter. The population mean is represented by mu and sample mean, as we have discussed in the previous lecture, is represented by x bar. Since mu is the population mean, it is a parameter, and since x bar represents the sample mean, it is a statistic. X bar is given by the function 1 by n summation of I equals to 0 to n x of I. This function is called as an estimator. An estimator is calculation from the sample that is used to estimate the population value. Now let us see the definition of unbiased estimator. An estimator is said to be unbiased if and only if the expected value of the estimator is equal to population parameter. Expected value means average. Remember, expected means average. That is, if the expected value of the sample mean is equal to the population mean. So now this expected value of sample means average of all the sample means will be equal to the population mean. See, we are not going to take only one sample. We are going to take a number of samples from this population. And each sample will have a different sample mean. So when we take an average of all the sample means, we will get the expected sample mean. And for an unbiased estimate, this expected sample mean will be equal to the population mean. Thus, we will be able to get the population mean by calculating the expected sample mean. In other words, if the expected value of sample mean is equal to the population mean, then the statistic is an unbiased estimate of the parameter. So expected value of the statistic is equal to parameter in case of unbiased estimate. This is what is called as unbiased estimate. And just for your information, if the expected value of statistic is greater than that of the parameter, it is called as a positively biased estimator. And if the expected value of the statistic is lower than the parameter value, then it is called as a negatively biased estimator. That's it for today. In the next lecture, we will cover standard error. Thank you.